Good afternoon, my name is Iván Coarasa and I will present the application of machine learning techniques to the 3 years of data from the ANAIS-112 experiment. ANAIS is a direct dark matter detection experiment aiming to provide a model-independent test of the signal reported by Dama Libra using the same target and technique at the Canfranc Underground Laboratory in Spain. ANAIS-112 is operating an array of 3x3 ultra-pure thallium-doped sodium iodide crystals with a total mass of 112 kg since August 2017. All the 9 modules are simultaneously calibrated with external cadmium-109 sources every 2 weeks. Inside the ANAIS hat, a modular similar to those of ANAIS was installed but without sodium iodide crystal. This blank module is coupled to 2 PMTs identical to those used in ANAIS-112 modules and is integrated in the ANAIS-112 DAC system. Its main goal is to study the different non-bulk event population that have their origin in the photomultiplier. And is that the trigger rate in the region of interest from 1 to 6 keV is dominated by non-bulk scintillation events. The filtering protocols developed to discriminate these noise events from real scintillation events are based on pulse shape and asymmetry. Firstly, time behavior compatible with sodium iodide scintillation constant is selected by means of a biparametric cut defined by P1 and the logarithm of mu. Secondly, light sharing between the 2 PMTs compatible with bulk scintillation is chosen by imposing more than 4 peaks in each PMT signal. This cut is so restrictive that limits the energy threshold to 1 keV. Although this filtering procedure works very well above 2 keV, the measure rate from 1 to 2 keV is about 50% higher than expected by our background model, and we cannot discard non-bulk scintillation events as responsible of that excess. In order to improve the rejection of noise events between 1 and 2 keV, we propose to use a machine learning technique. In particular, a multivariate analysis using boosted decision trees has been performed. This method allows us to combine several weak discriminating variables into a single powerful discriminator. Decision trees have a binary structure with 2 classes, signal-like and background-like events. Small values for VDT correspond to background-like events, whereas large values indicate signal-like events. We use AdaBoost to implement the boosting algorithm, which allows to stabilize the response of the decision tree with respect to fluctuation in the training sample. Following the strategy of ANAIS-112 filtering protocols, we separate the training into 2 phases. In the first phase, we try to extract the scintillation events considering input parameters only depending on the shape of the total pulse from the 2 PMTs. As training populations, low-energy cadmium-109 calibration events are used as a pure scintillation signal sample, whereas events from the blank module are used as noise sample. In the second phase, we use as input parameters those that describe the asymmetry in the light shading among both PMTs for low-energy events, to separate the signal from the noise. Again, cadmium-109 calibration events are used as signal sample, while physics run data are used as noise sample because they are dominated by PMT, noise-like events in the very low energy region. In particular, different variables related to church and time of the total pulse are used as training variables in the first phase. P1 and P2 represent the fraction of area of the tail and head of the pulse respectively. CAPX is the integral of the cumulative distribution of the total pulse up to x nanoseconds, and mu is the amplitude-weighted mean time of the individual photoelectrons' arrival times in the digitized window. After training, the output of the algorithm is encoded in the variable VDT. The distribution of the VDT variable is shown in this figure for cadmium-109 calibration events in red and background events in black in the 1 to 2 keV energy region. We can observe 3 peaks in the distribution of background events, around VDT equal to minus 0.45, mostly corresponding to fast PMT noise events, around minus 0.35 due to a very large mean time, and the peak observed around VDT equal to minus 0.05 associated with asymmetric events. The latter are not clearly distinguished from calibration events. If we plot how the VDT score is distributed as a function of energy, we see that events with energy above 2 keV are clearly separated into two bands. The upper one corresponds to scintillation and the lower one to noise. However, below 2 keV, both populations overlap. In the second phase of training, the following are used as input variables: the number of peaks detected by the peak finding algorithm in PMT0 and PMT1 traces, N0 and N1 respectively, and the quotient between the charge partition among both PMTs and the total charge, corrected by the corresponding mean value of asymmetry in area for each detector. The training result provides the new VDT2 variable, which combined with the previous VDT parameter allow us to discriminate most of noise events from scintillation events. Here are the two-dimensional scatter plots of the VDT versus VDT2 outputs for background data on the left and calibration events on the right in different energy regions are shown. Fast PMT noise events and events with very large mean time are easily removed using only the VDT parameter. However, we observe that for positive VDT values, a new type of events between 1 and 2 keV appear in the background data, which do not appear at higher energies nor in the calibration events, or at least not in the same proportion. For this reason, it is mandatory to use both VDT variables to be removed. Events that are above and to the right of the solid red lines in the figures are retained. These straight line cuts on VDT and VDT2 parameters have been optimized to ensure the lowest total background in 1 to 2 keV. We select VDT and VDT2 greater than 0.1 and the corresponding efficiency is estimated for each detector independently by using cadmium-109 calibration single hit events. In the figure on the left, we see in red the efficiency obtained with this machine learning method, and in black that obtained with the cuts defined in ANAIS. In addition, it is superimposed the efficiency calculated with the VDT technique from the coincidence events of sodium-22 and potassium-40, or from our recent calibration with neutrons. All of them are compatible with each other. After applying the filtering and the efficiency correction, the resulting rate has suffered a reduction of 26.5% between 1 and 2 keV with respect to that obtained with the previous event selection procedures. Comparing this result with our background model, we observe a 37% discrepancy between 1 and 2 keV versus to the 54% observed previously, so there are still unexplained events below 2 keV, which could be related either with non-bulk scintillation events which have not been rejected by our VDT2 filtering procedure, or some background sources which have not been taken into consideration in our model. More work is underway in order to develop additional procedures for the rejection of the remaining PMT noise events. Although the VDT-VDT2 method gives a good event separation between scintillation and noise events, the validation of boosted decision trees becomes mandatory to ensure that calibration events used in the training behave in the same way as background events. For instance, the validation of free variables used in training is shown here. We can observe that there is a good agreement in the shape of distributions for variables between cadmium-109 calibration events and the selected scintillation data. From the updated background, the efficiency estimate and the lifetime distribution, we can calculate the sensitivity projection of ANAIS-112 to the Gamma Libra signal. The sensitivity is given by the standard deviation of the modulation amplitude, and we express it as the quotient between the gamma signal and said standard deviation. It can be observed that the VDT technique improves moderately the expected sensitivity in the 1 to 6 keV energy region, as well as slightly in the 2 to 6 keV energy range. In particular, the VDT method improves the sensitivity between 1 and 6 keV by 11.6% and by 2.7% from 2 to 6 keV, with respect to that obtained with the established ANAIS-112 filtering protocols. Finally, the reanalysis of the 3 years of ANAIS-112 data searching for annual modulation using the BDT method is carried out. Performing a least square feet of the rate of events to this function, the following results are obtained. The null hypothesis is well supported by chi-square tests in both energy regions, with p-values approximately equal to 0.3 in both regions. For the modulation hypothesis, best fit modulation amplitudes compatible with 0 at 1 sigma are obtained in both cases. Plotting these results on the sensitivity curves estimated a priori, we observe that there is an excellent agreement. The present sensitivity is approximately 2.7 sigmas in both energy regions, and the 3 sigma sensitivity goal will be reached before the scheduled 5 years. This result can be further improved by considering the 9 detectors independently. Using this equation to model the rate of events of each detector separately, results consistent with absence of modulation at approximately 1 sigma are also obtained. The standard deviation of the modulation amplitude results to be 0.0032 counts per keV kilogram and day in 1 to 6 keV and 0.0034 counts per keV kilogram and day from 2 to 6 keV. Lastly, this figure summarizes the results obtained for the standard deviation of the modulation amplitude, that is, the sensitivity to the annual modulation signal for the different filtering protocols used. Those obtained with the ANAIS-112 established procedures are shown in black, whereas those derived from the application of the BDT method are shown in red. In both cases, the better results are obtained when segmented detector is considered. In particular, using the boosted decision tree implies an increase of 23.8% in the sensitivity between 1 and 6 keV, and an increase of 10.5% between 2 and 6 keV. To sum up, a new PMT-related noise rejection algorithm based on the BDT technique has been developed. A background level reduction of 26.5% has been achieved between 1 and 2 keV, but there is still a 37% discrepancy with our background model. More work is underway in order to develop additional procedures for the rejection of the remaining PMT noise events. The reanalysis of the 3 years of ANAIS-112 data taken with this technique has been presented. Results are consistent with the absence of modulation and confirm a sensitivity of 3 sigma to gamma Libra result even before the scheduled 5 years of data taking. Thank you for your attention.